In the quest to build intelligent systems, a key challenge is creating models that understand and predict the world around them, much like humans do. For years, the dominant paradigm in video understanding has been generative, focusing on predicting the exact pixel values of future frames. This approach, while powerful, is computationally expensive and often wastes resources on irrelevant details, like the precise rustle of leaves in the wind. Today, we explore a more efficient and abstract approach, the Joint-Embedding Predictive Architecture, or JEPA. We'll dive into its image-based origins with LE-JEPA and its evolution into the state-of-the-art video model, V-JEPA, uncovering how predicting in an abstract, latent space is unlocking a new generation of scalable and powerful world models. Let's first formalize the problem with pixel-level prediction. When a model tries to generate a future video frame, it's tasked with predicting the red, green, and blue values for every single pixel. The loss function, typically a mean squared error or L1 loss, penalizes any deviation. This forces the model to expend immense capacity on high-frequency, stochastic details that are often unpredictable and semantically meaningless: the exact pattern of rain on a window, the precise shape of a cloud. This is not only inefficient, but also misguided. True understanding doesn't require knowing where every photon will land. It requires grasping the underlying dynamics: the ball will continue its trajectory, the car will turn the corner. Generative models can get bogged down in the texture, potentially missing the compositional and semantic structure of the scene. This is where the Joint-Embedding Predictive Architecture, proposed by Yann LeCun, offers a fundamental paradigm shift. The core idea is to perform prediction in an abstract representation space. Instead of taking an input and predicting a future input, JEPA takes a representation of a context and predicts a representation of a future target. The architecture consists of three main components. First, a context encoder creates a representation of the input X. Second, a predictor takes this representation and estimates the representation of a different, but related, target Y. Third, a target encoder computes the actual representation of Y. The goal is to make the predicted representation match the actual target representation. This simple but powerful idea avoids the pitfalls of pixel space generation by focusing entirely on information that is predictable and semantically meaningful. The first concrete implementation of this idea for images was the Latent Energy JEPA, or LE-JEPA. It frames the prediction problem through the lens of an energy-based model, or EBM. The model learns an energy function that assigns low-energy values to compatible pairs of context and target representations, and high-energy values to incompatible pairs. Think of it as learning a landscape of possibilities. Given a context, like the bottom half of an image, the model's energy function creates a valley of low energy for all plausible top halves. A picture of the sky would result in a low energy score, while a picture of car tires would result in a high one. This EBM formulation allows the model to capture the multimodal nature of prediction. There can be many correct answers, and the model learns to identify all of them as plausible, low-energy outcomes. The architecture of LE-JEPA is a direct implementation of the JEPA philosophy. We have a context encoder, which processes a visible block from an image. We have a predictor, which takes the context representation and outputs a predicted representation for a different, unseen target block. And crucially, we have a target encoder. The target encoder's job is to compute the ground truth representation for the target block. To ensure the model learns meaningful features, the target encoder's weights are not updated through backpropagation from the predictor. Instead, they are updated as a slow-moving exponential average of the context encoder's weights. This stop gradient or momentum encoder trick is vital. It prevents the model from collapsing to a trivial solution where the encoder simply outputs a constant value that is easy to predict. The learning signal in LE-JEPA comes from a contrastive loss function. The goal is twofold. First, we want to minimize the energy assigned to the positive pair, which consists of the context block and the actual target block from the same image. This pulls the predicted representation closer to the true target representation. Second, we must prevent the model from assigning low energy to everything. To do this, we sample negative target blocks from other images. The loss function then pushes up the energy for these negative pairs, ensuring they are seen as incompatible with the context. A margin M is used to ensure that the negative energy is pushed up to be at least a certain distance away from the positive energy. This process sculpts the energy landscape, creating the deep valleys for correct predictions while keeping the rest of the landscape elevated. While LE-JEPA demonstrated the power of predictive learning on static images, the ultimate goal for a world model is to understand dynamics, causality, and the flow of time. This requires moving to the domain of video. Video presents a unique set of challenges and opportunities. The core task is no longer just spatial infilling, but spatiotemporal forecasting. Given a sequence of past frames, what will happen next? A direct application of pixel prediction models to video led to systems like Sora, which are incredibly powerful but also astronomically expensive to train. The JEPA philosophy, however, suggests a more efficient path. Can we learn the high-level dynamics of a video without getting bogged down in rendering every pixel? This question directly leads us to the Video Joint-Embedding Predictive Architecture, or V-JEPA. V-JEPA takes the central idea of JEPA and adapts it brilliantly for the video domain. The key innovation is how it formulates the context and target. Instead of predicting a missing patch in an image, V-JEPA predicts a missing segment of a video clip, but it does so entirely in latent space. The process is as follows. A video clip is passed through an encoder, which extracts a sequence of latent representations, one for each patch in space and time. A portion of this clip, typically the beginning, serves as the context. The model is then tasked with predicting the latent representations for a masked-out block of frames in the future. By masking large, contiguous blocks in spacetime, the model is forced to learn higher-level concepts. It can't cheat by interpolating from nearby patches. It must genuinely understand the motion and transformation of objects to make an accurate prediction. The V-JEPA architecture is both elegant and powerful, primarily built from standard transformer components. It begins with a backbone encoder, typically a vision transformer or ViT, which is applied to the raw video frames to extract patch-level embeddings. This is the X-encoder in the JEPA framework. These embeddings form our latent space. A subset of these embeddings, the context, is then fed into the predictor, which is itself another transformer model. The predictor's job is to attend to the context tokens and output a prediction for the embeddings of the masked target region. Concurrently, the full video clip is passed through the target encoder which, like in LE-JEPA, is a momentum-updated version of the X-encoder to get the ground truth target embeddings. The model is then trained to minimize the difference between the prediction and the target. The masking strategy in V-JEPA is not just a minor detail, it is central to its success. Unlike early masked autoencoders like BERT or MAE that used random, small masks, V-JEPA employs a block masking strategy. It masks out large, contiguous spatiotemporal blocks from the target. Why is this so important? Randomly masking small patches encourages the model to learn local, low-level statistics, basically, how to reconstruct texture by looking at adjacent patches. By removing a large, contiguous chunk of the video's latent representation, you remove all local information. The only way for the predictor to successfully fill in the missing representation is to have learned a higher-level, conceptual understanding of the scene. It must reason about object permanence, trajectory, and interaction to hallucinate the representation of what should be in that missing block. One of the most appealing aspects of V-JEPA, especially compared to its energy-based predecessor, is the simplicity of its loss function. Since the goal is to directly predict the target representation, we can use a simple regression loss. The model computes the L2 distance, or mean squared error, between the output of the predictor and the output of the target encoder, averaged over all the patches within the masked target block. That's it. There's no need for negative sampling or a complex contrastive objective. The difficulty of the prediction task itself provides a strong enough learning signal. The momentum target encoder ensures the target representations are stable and information-rich, preventing the collapse that this simple loss might otherwise suffer from. This simplicity makes the model more efficient and stable to train. Let's now explicitly compare the JEPA family to generative models that predict pixels, like GANs, V, or diffusion models. The fundamental difference lies in the prediction space. Generative models operate in the high-dimensional, noisy space of pixels. JEPA operate in a lower-dimensional, cleaned-up, and abstract latent space. This has profound consequences. Generative models must be perceptual, learning details that appeal to human vision. JEPA only need to be semantic, capturing the abstract information needed for the prediction task. This makes JEPA significantly more computationally efficient. They don't waste capacity modeling unpredictable noise, allowing them to focus on learning the underlying structure and dynamics of the data. This is a key reason for their scalability. It's also crucial to distinguish JEPA from another popular self-supervised method, contrastive learning, seen in models like SimCLR and MoCo. Contrastive methods learn by discriminating. They are given a positive pair, two views of the same image, and many negative pairs, and their goal is to pull the positives together in the embedding space while pushing all the negatives far away. JEPA is different. It doesn't just discriminate, it predicts. Instead of just being told this is the correct answer, the predictor model must generate the representation of the correct answer from the context. This is a much harder and more constrained task, which often leads to superior representations. It forces the model to synthesize information, not just recognize it. In essence, while contrastive learning asks, are these two similar? JEPA asks, given this, what does that look like? So, how does this all tie back to the grand vision of building a world model? A world model is an internal simulation engine that an AI agent can use to understand its environment and plan future actions. By learning to predict how the world evolves not at the pixel level, but at the level of abstract concepts, V-JEPA is learning precisely such a model. When V-JEPA accurately predicts the latent representation of a ball's future position, it has implicitly learned a model of gravity and momentum. When it predicts that a hidden object will reappear, it has learned object permanence. This abstract, predictive knowledge is exactly what's needed for an agent to reason and plan. It doesn't need to render the future in its head. It just needs to know the future state of the important variables, which is what the latent space captures. The architectural choices of V-JEPA lead to remarkable scalability and efficiency. The primary reason is the reduction in dimensionality. A short video clip can easily contain tens of millions of pixel values. A corresponding latent representation might only have a few 100,000 dimensions. Performing prediction over this much smaller set of values is drastically faster and requires less memory. This efficiency means V-JEPA can be trained on more data, with larger models, and for longer, than a comparable pixel prediction model. Furthermore, since the predictor only sees the small context and predicts the small target, the computational load of the most complex part of the model doesn't scale with the full video length, allowing for efficient processing of long video sequences. This is a critical advantage for building models that can understand long-range temporal dependencies. A self-supervised model like V-JEPA is not an end in itself. Its primary value lies in the powerful, general-purpose visual representations it learns. Once V-JEPA is pre-trained on a massive dataset of unlabeled videos, its encoder can be used as a feature extractor for a wide range of downstream tasks. For example, you can take the learned representations, attach a simple linear classifier, and fine-tune it for action recognition with very little labeled data. The features have been shown to be incredibly effective for tasks like object tracking and video segmentation. The rich understanding of dynamics also makes the V-JEPA encoder an excellent perceptual front-end for a reinforcement learning agent, providing it with a robust state representation of its environment. This transferability is the ultimate test of a self-supervised model's success. Despite its successes, V-JEPA is not without limitations. The quality of the learned representations is highly dependent on the target encoder. The momentum encoder design works well, but might not be optimal. The model's predictions are also deterministic, outputting a single predicted representation. Future work could explore probabilistic predictors that can capture the inherent uncertainty of the future, perhaps by outputting a distribution over latent space. The most exciting future direction is multimodality. Imagine a JEPA that takes video and text as context and predicts the latent representation of future audio. Such a model would develop an even more holistic understanding of the world, connecting visual events with their sounds and descriptions. This cross-modal prediction is a promising frontier for building more comprehensive world models. In summary, the Joint-Embedding Predictive Architecture represents a pivotal shift away from the computationally burdensome task of pixel generation and towards the more efficient and scalable paradigm of abstract, latent space prediction. From the energy-based foundations of LE-JEPA to the streamlined and powerful V-JEPA, this approach has demonstrated a remarkable ability to learn semantically rich representations of the visual world. By forcing the model to predict what matters, not just what is visible, JEPA learns the underlying dynamics of our world, paving the way for more capable, efficient, and scalable AI systems. The future of AI may not be about rendering a perfect picture of tomorrow, but about forming an abstract, intuitive understanding of what tomorrow might hold.